This is a very important and very interesting open source and citizen science project that would like to have a lot of participants involved to study some of these hypotheses. What it is carbon sequestration as a way of putting carbon back into our soils and taking it out of the atmosphere. Carbon could actually stay in the soils for centuries to millennia in the form of biochar. And this could actually be produced by agricultural biomass waste. And very easy to do. I'm going to be showing you how to set this up. But a good friend of mine, Jack Sorrell, of Plenty for All, he's actually made a biochar stove, and it's very low tech and very effective. He makes 30 pounds of it during a burn. It's produced by a process called pyrolysis, which is a slow combustion in a low oxygen environment. So like a lot of the biomass, all the hydrogens and oxygens are actually burnt off first. And most of the carbon, 50% of the carbon actually still stays intact, and it still keeps a lot of the characteristics, the cellular characteristics of the wood. A gram of that could actually have the surface area of this room. So we could actually produce a flammable gas that could be used for heating and cooking. Ancient indigenous cultures in the Amazon basin, over 2,000, 1,000 years, have actually incorporated biochar into the soil and into their agricultural activities. And their soils are still incredibly productive, even till this day. So this works. We have to study how biochar in the soils changes the soil properties. Like there is not a lot of work on this. I'm actually using activated carbon as a proxy for biochar because I was not able to find it, even asking experts. So this is brand new, and I think this will be a game changer for climate change. Biochar has the potential of harboring bacteria that can break down ammonia, N2O, NO2 minus, various nitrogen oxides that are pollutants, and it could actually harbor bacteria that will fix them into a fixed form, NO3, which is essential for plants. And like it captures those pollutants. Activated carbon is actually used for gas masks, for VOCs and that. It also improves the cation exchange capacity of the soil, which is vital, so plants could pick up metallic ions. And it stabilizes the pH, and it also holds water. So it's good in drought conditions. There is actually more carbon stored in our soils than in the atmosphere and the vegetation. And like a crop that's actually grown organically and with permaculture, it has been estimated that the bacterial culture, the fungus, like the roots and that, without biochar alone, will actually sequester a ton of carbon over an acre per year. This actually speeds up the process, and like we could actually take out a massive amount of carbon just by tweaking our agriculture just a tiny bit. No-till like agriculture, you're not disturbing fungal habitats. You're not disturbing insects. You're not. These organisms are essential for healthy soil, and it actually helps take nutrients from the biochar and give it to the plant in the right amount. Okay, now like we're going to do a very simple setup here. We're going to bring all these concepts and all these science, and there's a whole bunch of other stuff I could throw at you, because I'm really impressed and excited about the potential of this. So what we could do is put this all in this pot. And essentially what we're going to be doing is, like I have an aquarium air pump, it's a diaphragm with an air hose. So I got a little pod at the local Rona, cost me $11. And I'm just going to put the air plug here. I have some aquarium gravel to dissipate the air. So what we're going to be doing is actually reverse engineering the famous NASA study. So this plant pot will actually clean air, and it will actually take the pollutants and make them available to the plant, like all those nitrogenous oxide and ammonia compounds that we don't really want in our house, but it'll make fertilizer. So we won't have to fertilize it. And then I have some rock materials. This is actually a highly prilled basalt. It's volcanic rock. It's full of metallic elements, silica. It really strengthens up the plants. And here's some dolomitic limestone, which is calcium carbonate and magnesium carbonate. Because we have to remember, magnesium is essential to make chlorophyll for the plant. Chlorophyll is very similar to hemoglobin, but it's, instead of being iron-based, it's magnesium-based. This is going to help out the plant greatly. This is a mycorrhiza. It's a fungus that actually attaches onto the root system of the plant, lives off the sugar, and has a protein that doesn't decompose. And they might live like for a couple weeks and grow like an inch, but they actually take all these metallic elements and phosphorus. So like we have a proxy for calcium phosphate. It's in a soluble form, it's in a non-liable form, so it'll stay in the soil. And with the biochar and the mycorrhiza, it'll make it available to the plant. So this will actually prevent fertilizer runoff from farm fields, which are a huge source of phosphate contamination in lakes and nitrates. Like we have the problems in Lake Erie. My friend Jack could tell you more about it. Like the Mississippi River, it's like our soils are being stripped bare, but one of the things about biochar, it'll sequester these nutrients into the soil. So that's another thing I'm very excited about. So what I'm going to do is just empty this into the pot. So like I don't want to have a stream of air going directly. I want it to be diffused. I put a couple of holes here so we can have water exchanging. The water will go up, and so the water won't stagnate. So it's very important that for the root system and the soil that we have a lot of oxygen. So we're going to avoid root rot. And what that will do, it'll help us to give a wide margin of error in looking after our plants. So like we could, if we overwater, it won't be such a big deal. And then like I'm going to mix my biochar, which has been sitting in water and that. And we're going to Yeah, I was charging it with the rock dust. Like over a couple nights and that, making sure it has a maximum amount of water and nutrients, and get a starter colony of beneficial microbes to interact with the nitrogen cycle. And then we'll add a tiny bit of dolomitic limestone or calcium carbonate. Yeah, like calcium carbonate is a huge amount of carbon too in there, right? Like actually, when calcium carbonate is reacted with acids, it actually produces carbon dioxide. So acid rain on concrete structures, like even on bedrock, will cause like some carbon. So I'm just adding a bit of phosphorus. I'm just eyeballing this. It just to start off, but people that are more scientifically inclined, like they could actually fool around with exact recipes and exact amounts. So we have our 3 minerals, which are very important because that's another thing that agriculture has forgotten is actually the relationship between the geology of the earth. I added peat moss. It actually is a very good absorber of water. It's actually nutrient deficient, so there's not there's no barely any nitrates or nitrogen because we're actually going to get that from the air by bubbling the air through the air pump. But peat moss is very important. It's acidic. It also has these chelating acids like humic, tannic, and fulvic acid that could actually bind to metallic ions like iron, copper, magnesium, zinc, vanadium, molybdenum, cobalt. Like plants all need this in manganese. They need this in small amounts. And so it's like we're just testing to see if we can make an autonomous plant pot that doesn't need any fertilization, and like drawing air through it, like the root system should be healthy, and we don't really have to worry about overwatering as much. So like we have a plant pot that could clean air and could naturally provide everything a plant needs. So I have to make sure I don't add too much basalt. I really love this stuff, but it turns into a clay, so it might impede the water going through. So I'm just adding a bit more, and phosphorus and magnesium. Yeah, that will kind of, like that's a good pH buffer. Magnesium and calcium carbonate, and yeah, it should be. Mix it around a bit and should be ready. So I just pack it into my plant pot, and so it's a very granular soil. Like air could actually go through it and water in that. And like I'll see what happens. It just it's always a trial and error, right? I haven't got the exact recipe down, but this could be really important to educate and test the property of these natural materials. And we're actually making soil like in a pot, and actually cleaning the plant at the same time. Like we have another prototype that we put together maybe 9 months ago. It's doing well. Like the plant, the leaves are well fertilized. Like I use the spathiphyllum that I used to use to judge fertilizer content, because if there's a lot of nitrates, the flowers would turn green. So, yeah. Okay. Yeah, I should just. I have to make some more and fill this up, but I'll be taking this home and making a nice plant pot. I bought some LEDs, like 50,000 K. They're almost full spectrum, like the sun, and yeah, I should have a nice little interior plant, clean out the air, and this could be done quite simply. As this is open source, and this concept was actually from the famous NASA study from 30 years ago, it's important that this gets out and people fool around and people criticize whether it works or not. Comment in the video, and we could share stories on what works and what doesn't. And I have not seen anything like this. I did quick Google searches, and this is really overlooked. Carbon sequestration with biochar.